Okay, so I've got a few requests to solve some of the exercises from the course notes. So let's start with the first one. So this is question number 23 from chapter 5. How many positive divisors does 2 to the 5 times 3 to the 4 times 5 to the 3 have? Okay, so this is one of these questions which really just boils down to the fundamental theorem of arithmetic. So suppose that, so basically let's talk about how to kind of work this out. So suppose that D is a divisor of this number. Now, if you think about it, what are the primes in the prime factorization of 5? Well, and if you kind of think about it, like D can only have, in its prime factorization, the numbers 2, 3, and 5. And the exponents can't be bigger than, the exponent of 2 can't be bigger than 5, the exponent of 3 can't be bigger than 4, and the exponent of 5 can't be larger than 3. And this is, again, just really boiling down to the fundamental theorem of arithmetic, because if D was divisible by like some other prime, then that prime would also divide this number, but this number has a unique prime factorization, and 2, 3, and 5 are primes, so that would be a problem. So basically, no matter how you kind of slice it, like D has to have the form 2 to the x, 3 to the y, 5 to the 3, or sorry, 5 to the z, for some integers x, y, and z, such that x is between 0 and 5, y is between 0 and 4, and z is between 0 and 3, by the fundamental theorem of arithmetic. And now basically, the number of ways to choose a divisor, D, is the number of ways of choosing x, then choosing y, and then choosing z. I should also maybe point out that, like, any choice, or maybe I'll just say any two choices of x, y, and z give different numbers, or let's say divisors, D, again, by the fundamental theorem of arithmetic. Like, if I make a different choice of x, y, and z, it can't give me the same number, because then you'd have a number that has two different prime factorizations, but that's not possible. Anyway, at the end of the day, the number of choices for D is equal to the number of choices for x, y, and z, which is like, there's 6 ways to choose x, 0, 1, 2, 3, 4, and 5. Then there's 5 ways to choose y, and there's 4 ways to choose z. So it's whatever this is, like 120 or something. Okay, and that would be your final answer. Okay, so let's move on to the next question. Okay, so this is again from chapter 5. It's question number 24. Suppose a and b are integers such that a times b is negative 2 to the 7, 3 to the 8, 5 squared, 7 to the 6. And the GCD is 2 to the 3, 3 to the 4 times 5. The question is it possible that a is equal to 2 to the 5, 3 to the 4 times 5? and then it asks what is the LCM of A and B. Now, frankly, it's a little bit of a strange question, but let's answer it anyway. So suppose A is equal to 2 to the 5, 3 to the 4 times 5, and A times B is equal to negative 2 to the 7, 3 to the 8, 5 squared, 7 to the 6. I mean, now we can just get B, right? So B is negative 2 to the 7, 3 to the 8, 5 squared, 7 to the 6, divided by A. We know what A is. It's just 2 to the 5, 3 to the 4 times 5. So B is just, by canceling some exponents and stuff, B is negative 2 squared, 3 to the 4 times 5 times 7 to the 6. Okay, and now if we think about it, the answer is no, right? To the first part, because if A is equal to 2 to the 5, 3 to the 4 times 5, then, well, B would be equal to this. And what's the GCD of A and B? Well, you want to take, the number 2 and take the smallest exponent, which is a 2. You take the number 3, take the smallest exponent, which is a 4. Take the number 5, take the smallest exponent, which is a 1, so 5 to the 1. And then 7, well, there's no 7 up here, so it's 7 to the 0. So basically, and I should, well, yeah. So basically, yeah, if A was equal to this, and A times B is equal to this, then the GCD, well, is 2 squared, 3 to the 4, 5 to the 1, which is not this number, right? So the answer is no to the first part of this question. Well, and if you want an answer, it's just because, I mean, if A is equal to this and A times B is equal to this, then B is equal to that, I mean, just by dividing. And so the GCD wouldn't be what this thing says it is. I guess there's not other ways you could explain that as well, but anyway. Okay, what is the LCM of A and B? I don't really, at this point, know what the question's asking anymore, because is it saying under the assumption that A is equal to this? I guess not. So I guess for the second part of this question, we're assuming that A times B is negative 2 to the 7, 3 to the 8, 5 squared, 7 to the 6, and GCD of A and B is 2 cubed, 3 to the 4 times 5. And we're trying to figure out what is the LCM. And we've got this thing that, if A and B are positive, which they're obviously not because there's a negative here, but if they were, then you're usually supposed to have GCD of A and B times the LCM of A and B should equal A times B. But this time we've got a bit of an issue because there's a negative here, but I mean, for negative numbers, you should just have something like this. So if we just plug in, so 2 cubed, 3 to the 4 times 5, LCM AB equals 2 to the 7, 3 to the 8, 5 squared, 7 to the 6, cancel stuff out, and then we get LCM AB is 2 to the 4, 3 to the 4, 5, 7 to the 6. Okay, that's just by dividing this over to the other side and canceling out the exponents. Okay, so that's how you do that one. Okay, so next we've got number 37 from chapter 5. We'll start with part A. So b is a integer which is greater than 1. And n is, dk minus 1 dot dot dot, d1, d0 in base b. And then I want to show that b minus 1 divides n if and only if b minus 1 divides the sum of the digits of n in the base b representation. Okay, so this is exactly the same as the divisibility by 9 thing that we did in class. So the key is here that, well, n is equal to dk b to the k plus dk minus 1 b to the k minus 1 plus dot 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 down to d1 b to the 1 plus d0 b to the 0. How did I get this? Well, this is just what this means. Okay, so literally writing n equals this thing just means that n is equal to this. Okay, it doesn't mean anything else. So if it's not clear to you where I got this equation, you might want to go back and review the base b representation stuff. Okay, now I want to kind of think about this modulo b minus 1. And note that, the key thing we're going to be using here is that b is congruent to 1 mod b minus 1. Right? So therefore, in fact, any power of b, so let's say b to the L, is 1 to the L, which is just 1 mod b minus 1 for all L between, let's say, 0, and infinity. So for all L in the integers where L is at least 0. Okay, so if I was to take this expression modulo b minus 1, this first term is just dk b to the k, and the b to the k can be replaced by a 1 when we're working modulo b minus 1. So this is just dk plus dk minus 1 plus dot 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 plus d1 plus d0. So this only makes sense if I'm working modulo b minus 1, right? Because all of the powers of b, by this thing that we said here, they can all be replaced by a 1, right? So therefore, since n is congruent to the sum of its digits mod b minus 1, and a number is divisible by b minus 1 if and only if it is congruent to 0 mod b minus 1. So therefore, b minus 1 divides n if and only if n is 0 mod, I'm a bit tired, I'm writing the wrong symbols here. So if and only if n is congruent to 0 mod b minus 1, if and only if, since n is congruent to the sum of the digits, so n is congruent to 0 mod b minus 1 if and only if dk plus dk minus 1 plus dot 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 d1 d0 is congruent to 0 mod b minus 1, which holds if and only if b minus 1 divides this sum. Okay, good. So that does part A. And now let's think about part B. Okay, so for part B, this hint is really kind of important here. The key here is that 10 is negative 1 mod 11. So again, we're just going to say, n is dk 10 to the k plus dk minus 1, 10 to the k minus 1, plus dot, 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 let's say 10 squared, d2 10 squared, plus d1 10 to the 1, plus d0 10 to the 0. And we're told that 10 is congruent to negative 1 mod 11, which is kind of clear, right? And then, so therefore, if I take 10 to the k, it's congruent to negative 1 to the k mod 11. So therefore, 10 to the k is congruent to 1 if k is even, negative 1 if k is odd. Right? So therefore, we can take this thing and, so this is all congruent to dk negative 1 to the k. We can just plug in, right? dk minus 1, negative 1 to the k minus 1, plus dot, 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 down to, and let's say, d2, negative 1 squared, plus d1 times negative 1, plus d0 times negative 1 to the 0. Okay, and so this is, we can just rearrange this basically to say that this is d0, so I'm just taking this from here. This is a negative 1 times d1, so it's minus d1 plus d2 minus d3, plus dot, 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 up to plus negative 1 to the k dk. Sorry, this was all mod 11. Yeah, this is mod 11. And again, n is congruent to this thing, mod 11, therefore 11 divides n if and only if 11 divides this sum, just like in the previous question. Okay, so there's a few steps to kind of write that out again, but it's exactly the same as what I wrote in the previous question, pretty much. So let's do part C. So this is kind of asking you to kind of spot the pattern and that kind of thing. So so basically, we want to generalize part B to some kind of statement for a base b bigger than 1. So let's say we take for b bigger than 1, we want to kind of get an idea of what is part B saying? What if I change the number 11 to the number 15, or I change the 10 to 7 or something. Right? If I change the 10, the base 10 to base 7, then if you think about it, you want to change the 11 to an 8 because 7 is negative 1 modulo 8, and then everything's going to work in the same way. So the statement of the generalization is for b bigger than 1, if n is equal to dk minus 1 dot, 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 d1 d0 mod b, sorry, not mod, base b, then b plus 1 divides n if and only if b plus 1 divides this alternating sum d0 minus d1 plus d2 minus dot 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 up to plus negative 1 to the k dk. Okay. So that's what you were asked to do in part C. It just says to state it. It doesn't say you have to prove it. So, but if you did want to prove this, you would just follow the same steps as in the previous two questions, basically, and it's going to work. Okay, so that finishes off that question, and let's move on to another one. Okay, so here's question 16 from chapter 4. Guess and prove a formula for the kind of sum, like 1 minus 2 plus 3 minus 4, up to like plus negative 1 to the n minus 1 times n. And this, you're kind of given a hint that the formula might be different if n is even or n is odd. So to be honest, you haven't really been given much in terms of like methods to do this, but it doesn't turn out to be very hard. So let's kind of try to guess a formula. So basically, part of this question is really about trying to see the pattern and see if you can prove that it's true. So for n equals 1, so let's just do the odd numbers first. So for n equals 1, I get 1, right? Because this sum will just have the number 1 in it. For n equals 3, I get 1 minus 2 plus 3, which, I mean, 1 minus 2 is negative 1. I add 3, so it's 2. For n equals 5, got 1 minus 2 plus 3 minus 4 plus 5. Now let's try to be a bit clever here, right? The thing is, I already know the answer to this. 1 minus 2 plus 3, I already computed previously that that's equal to 2. Then if you think about it, the remaining stuff just adds a 1, right? Because it's negative 4 plus 5. And actually, if you write down another one of these, you'll see that the same pattern keeps holding, right? So it's like 1 minus 2 plus 3 minus 4 plus 5 minus 6 plus 7. And I take this part, and I already know this evaluates to 3 because I already did it. Then it's going to subtract 6 and add 7. But if you subtract 6 and add 7, you basically just added 1, right? So that's 4. So I'm guessing that for odd n, the answer is going to be like, well, whatever this kind of tracks as. So it's basically like n plus 1 over 2. So my guess, if n is odd, the answer is n plus 1 over 2. Okay, we have to prove that still. But in terms of coming up with a guess, I think if you just write down a few terms and then figure out the pattern, I think that's the right thing to do. Let's think about even values of n. For n equals 2, we've got 1 minus 2, which is negative 1. For n equals 4, we've got 1 minus 2 plus 3 minus 4. Again, we can kind of break this down. We already know 1 minus 2 is negative 1. And now I'm going to add 3, but subtract 4. But that's the same as subtracting 1, right? If I add 3 and subtract 4, that's like, effectively it's just subtracting 1. Let's do n equals 6, 1 minus 2 plus 3 minus 4 plus 5 minus 6. Again, most of this is just like what I computed before, and then I subtract 1, so it's like minus 3. So I think we can guess that if n is even, the answer is negative n over 2. Right? Because I got negative 1 when I put in 2. When I put in 4, I get negative 2. It seems like the pattern is probably correct. Okay, but we still need to prove this. So, okay, so to make our life a little bit easier in proving this, let me, I guess, turn it into a slightly different statement. So what we've kind of determined is that the answer should be n plus 1 over 2 if n is odd, and negative n over 2 if n is even, which is admittedly kind of an annoying expression. But what if we if you think about it, we can kind of simplify this a bit. So, well, not simplify it, but kind of merge it into one expression. So I'm going to write this as negative, well, basically, if n is odd, this is pretty much n over 2. And if it's even, it's kind of like negative n over 2. To make that work out, right, this function will be n over 2 if n is odd, and negative n over 2 if n is even. However, this still isn't the correct thing because we need the 1/2 in the case when n is odd. Now, frankly, it's not that obvious how to do this, but I mean, if you think about it and kind of try to reverse engineer it, like, what are we going to get here? Right. So to kind of explain what I'm trying to do here, I want a function, basically I want this term to be 1/2 when n is odd, and I want it to be 0 when n is even. Now, the way I can kind of set that up is like, if n is odd, I want to get like a 1 over 2, which is the same as 2 over 4. So if I've kind of got this, this negative 1 to the power n minus 1, if n is odd, the exponent will be even, so it's 1 plus 1 over 4, which gives you 1/2. If n is even, then n minus 1 is odd, and then these 1's cancel, and you get 0 for this, right? Yeah, I don't have a really great way of coming up with that. It's just, yeah. The nice thing about negative 1's, right, is if I take exponents of negative 1's, it keeps switching back and forth from 1 to negative 1, 1 to negative 1. Turns out that that's a useful thing here. Anyway, what I want to prove now is that 1 minus 2 plus 3 minus 4 plus 5 dot 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 plus negative 1 to the n minus 1 times n is equal to negative 1 to the n minus 1 times n over 2 plus negative 1 to the n minus 1 plus 1 over 4 for all n at least 1. Okay, and our proof is going to go by induction. So by induction on n, the basis, as usual, is pretty easy. So the basis will just say that we're just going to deal with the case n equals 1. So let n equal 1. Then the left-hand side of the equation, by which I mean this equation, right, is equal to 1. And the right-hand side is equal to negative 1 to the 0 times a half plus negative 1 to the 0 plus 1 over 2. If you calculate that, you get a half plus, oh sorry, this 2 is supposed to be a 4, plus 2 over 4, which is 1. So left-hand side equals right-hand side when n is equal to 1. Okay, next we want to do the inductive step. Okay, so for the inductive step, let's just use weak induction because there's no point in using strong induction for this. So I'm just going to say let n be at least 1 and assume that 1 minus 2 plus 3 minus dot 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 plus negative 1 to the n minus 1 times n is equal to negative 1 to the n minus 1, n over 2, plus negative 1 to the n minus 1 plus 1 over 4. Okay, we just assume that the thing we want to prove is true for one specific value of n. And now we want to prove that it's true when n is replaced with n plus 1. Sorry, this was the inductive hypothesis, not the inductive step. This is my inductive step. So consider n plus 1. Now our left-hand side of this thing is 1 minus 2 plus dot dot dot, all the way down to, now if we plug in an n minus 1, well actually let's write down two terms. Let's write negative 1 to the n minus 1 times n plus negative 1 to the n times n plus 1. Right, because this is what I get if I plug in n plus 1 for n. Okay. Now the first part of this whole thing, we know what it is equal to by the inductive hypothesis, right? So this gives us negative 1 to the n minus 1, n over 2, plus negative 1 to the n minus 1 plus 1 over 4, and then we've still got this thing from before, negative 1 to the n plus 1 by the inductive hypothesis. Okay, so this is going to require a little bit of fiddling around. Okay, so let's kind of move some things around a bit. So I'm going to keep this thing here, and I'm going to kind of, so I'm going to break this up. So this thing here can be broken up into a negative 1 to the n times n plus negative 1 to the n, right? And I'm going to take this negative 1 to the n and kind of combine it with this thing here. So try to stay with me here. So I'm taking this, and now this is negative 1 to the n times n, which is the same as negative 1 to the n minus 1 times negative n. So I'm going to kind of bring this over here. So I've got a negative n here. Okay, and the rest of what I've got left is negative 1 to the n minus 1 plus 1 over 4. And I've still got this thingy here, right? So plus negative 1 to the n. Okay, so what this gives me is now something like negative 1 to the n minus 1. Sorry, actually, so what's happening in here, right? We get an n over 2, but now it's, and then it's minus n, so it's like a negative n over 2. So that negative can be kind of absorbed into this to give me negative 1 to the n times n over 2. And then I've got a negative 1 to the n minus 1 plus 1 over 4 plus negative 1 to the n. And frankly, things aren't looking that good, which is kind of annoying, but we can kind of fix this. Basically, you should always keep some idea about where you're going, right? So where are we trying to get to? So this I'm going to write on the side in green. Okay, so this is not like part of this, what I'm writing here, but like where we're trying to get to is like the expression on the right-hand side, but with an n plus 1 instead of an n. So we're trying to get to like negative 1 to the n plus 1 over 2 plus negative 1 to the n plus 1 over 4. Okay, we've made some progress in that direction, but it doesn't quite look right. Let's try to fix it. So I'm going to keep going with this calculation. So what I want to do, I want to get this to be an n plus 1 over 2 here. To do that, I'm going to kind of, I mean, you know, I kind of want to bring part of this into there. So, I mean, I don't want to collect these terms because that'll give me an n over 2 plus 1. But I want to break this one into two halves and then kind of collect terms in some sense. So, I mean, it might seem like I'm doing these magical manipulations here, but these things are not magical. Like, there is some intuition here that's guiding me, right? You know, it's not just based on just random algebra here. I'm trying to get to a certain destination, right? I'm trying to get to this and trying to see what I need to do to get there. So anyway, I can kind of collect terms here and get a negative 1 to the n over 2 plus a half, so it's n plus 1 over 2. That's good. And then I'm going to collect up these things together to get negative 1 to the n minus 1 plus 1 plus 2 negative 1 to the n over 4. Okay, if you think about that, this is how, if you got these on the same denominator, this is what you would get. Now here's the thing, negative 1 to the n is negative 1 times negative 1 to the n minus 1. So these things kind of cancel. And what you're left with, well, they don't cancel, but because there's a 2 here, it kind of more than cancels. So what you're left with is negative 1 to the n here plus 1 over 4. Turns out that's exactly what we wanted. So this is equal to the right-hand side. So that concludes the inductive step. And then the conclusion is just that the thing that you wanted to be true is true. So 1 minus 2 plus 3 minus dot 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 plus negative 1 to the n minus 1 times n is equal to negative 1 to the n minus 1, n over 2 plus negative 1 to the n minus 1 plus 1 over 2, 4, for all integers and at least 1. Okay. So I just realized you probably weren't able to see some of that calculation because my head was in the way. So let me just kind of sit here for a second and yeah, let you see the calculation. Okay, so let's move on to this next question, which is question 2 from chapter 2. It's got a couple of typos in it. But yeah, so it says, explain why the statement for all x, p of x, and q of x is logically equivalent to, and here's where the missing bracket is, so for all x, p of x, and for all x, q of x. Okay, and yeah, I mean, I guess it's kind of evident if you think about it, but basically for any x, for some x, like in order for p of x and q of x to be true, well, so it is true if and only if p of x and q of x are both true, right? And since that's the case for every single x, like the only way for p of x and q of x to be true for all x is if p of x is true for all x and also q of x is true for all x. So therefore, p of x and q of x is true for all x if and only if p of x and q of x are both true for all x. Okay. So that's part A. Part B is kind of similar, right? It's kind of the same thing, but with ors and with exists. So, but also, so another way you can do this, a really cheap way, is, essentially, this is, like if I take the negation of this thing, by De Morgan's and by the rules of negating things with quantifiers, this says for all x, not p of x and not q of x, which by part A is the same as for all x, not p of x, and for all x not q of x, right? Because that's what part A will tell us. But then this is the same as pull out the negations from both of these things and then use De Morgan's. So this is the negation of there exists x, p of x, or there exists x, q of x. Okay, so what we've shown is that the negation of the left side, like this thing, is equivalent to the negation of this thing, which means that the original thing is also logically equivalent to the other, this thing over here. So, so yeah, you could say this in words like we did part A, or you can just use part A and De Morgan and basic rules of negation to get part B. Okay, so see you in the next video if there is one.